Welcome to the Sleepy Science channel. Here, we use soothing sleepy bedtime science stories to unveil the tranquil mysteries of the universe for you. Tonight, let's relax our minds and embark on a gentle journey into a world of science and dreams, surrounded by the 430 Hz Earth frequency. Both universes start from a low entropy state at the Big Bang and evolve toward higher entropy. The total entropy of both remains balanced. The mirror universe might be filled with antimatter rather than ordinary matter. Antiparticles have opposite charge and magnetic properties compared to ordinary particles. When matter and antimatter meet, they annihilate, releasing pure energy. In the mirror universe, stars are made of anti-hydrogen, anti-helium, etc. These anti-stars shine as brightly as ordinary stars, following the same nuclear fusion processes. Anti-planets orbit anti-stars from a distance. These solar systems would look identical to ours. If intelligent life evolved in the mirror universe, that life would be made of antimatter. They would consider their reality normal, and our matter universe an alien, strange world. The mirror universe theory explains some cosmic puzzles. It explains why there's so little antimatter in our observable universe. It provides a natural explanation for the arrow of time without needing special initial conditions. Some scientists speculate that dark matter in our universe might be ordinary matter from the mirror universe. Gravity can travel between the two realities, while electromagnetic interactions are separated. The mirror universe is just one example of parallel realities that might exist in higher dimensional space. Our three-dimensional perception limits our understanding of these realities. Space might curve inward like an infinitely extended saddle surface, but most people imagine space as flat, like an infinitely extending sheet with straight lines extending in all directions. Einstein's general relativity shows massive objects curve space, creating the gravity we experience. But the overall shape of space itself depends on the total amount of matter and energy it contains. On the largest scales we can observe, the universe appears flat. Parallel lines remain parallel on cosmic scales. The angles of a triangle add up to exactly 180 degrees. This flat space extends throughout the observable universe and likely continues far beyond our view. But other bubble universes might have evolved completely different spatial geometries. Imagine a universe with negative curvature, where space curves outward like a hyperbolic saddle. In this reality, parallel lines would gradually diverge as they extend. The angles of a triangle would sum to less than 180 degrees. The shortest path between two points would be a curve, not a straight line. Navigating in negatively curved space would be profoundly confusing. Objects seeming to move in straight lines would actually follow curved trajectories. Light rays wouldn't travel parallel, they'd spread apart. This geometry would dramatically affect cosmic structure. In flat space, matter clumps under gravity to form stars, galaxies, and clusters. Negative curvature would hinder gravitational clustering. It would constantly stretch distances between objects, making it hard for galaxies to form and maintain spiral structures. Stellar systems would become unstable as orbital mechanics follow hyperbolic paths instead of ellipses. The cosmic web of dark matter connecting galaxy clusters in our universe might not form at all in a negatively curved, bubbly universe. Advanced civilizations in such a universe would need to develop completely different technologies. Their mathematics would be based on hyperbolic geometry, not Euclidean geometry. Their understanding of physics would need to incorporate the effects of spatial curvature into every calculation. Some theoretical models suggest our universe might contain small-scale regions of negative curvature. We cannot currently detect these hyperbolic regions. Might be relics from cosmic inflation or formed by exotic matter with peculiar gravitational properties. Negative curvature might also exist in extra-spatial dimensions it cannot directly perceive. String theory predicts reality might contain 6 extra-spatial dimensions. These dimensions are curled up so tightly they appear as points from our 3D perspective. If some of these extra dimensions have negative curvature, they might influence the behavior of fundamental forces and particles in ways we can't easily comprehend. Spatial geometry is just one aspect among infinite possible variations that the eternal inflation machine can produce. In the time it took you to read this sentence, trillions of new universes have been born. The inflation that created our bubble universe never truly stopped. It continues throughout the infinite multiverse, constantly stretching space and spawning new realities at an ever-increasing rate. This eternal inflation machine follows simple rules, yet generates infinite complexity. Its operating principle is as follows. The inflationary field exists everywhere in the multiverse. It drives exponential expansion of space by stretching it faster than light. Within the inflating space, in small, randomly distributed regions, quantum fluctuations cause the energy of the inflationary field to be higher or lowered than average. When a quantum fluctuation lowers the inflationary field's energy below a certain critical value, inflation stops in that region. The energy of the inflationary field transforms into matter and radiation, triggering a small-scale Big Bang that eventually cools to form stars, galaxies, and possibly even life. Meanwhile, inflation continues in the surrounding regions. The volume of inflating space grows exponentially, creating more regions where new bubbles can form. This process creates a self-sustaining, infinite loop, constantly reproducing universes on an unimaginable scale and number. Every second, the total volume of inflating space grows by a huge factor of 10. Within this exponentially expanding space, the rate at which quantum fluctuations spawn new bubbly universes is beyond human comprehension. It's like cultivating bacteria in an infinite petri dish that doubles every second. No matter how fast the bacteria reproduce, the available space grows even faster. The inflation machine works similarly. It constantly creates new cosmic territory for bubbly universes to form in. Each bubbly universe is born in cosmic isolation, evolves and dies once a bubble forms. The surrounding inflating space moves it away from other bubbles at superluminal speeds. Bubbles cannot send signals to other bubbles, nor receive information from the wider multiverse. Each reality evolves independently according to its own randomly determined physical laws. but the eternal inflation machine ensures that every possible combination of physical laws will eventually be realized somewhere in the multiverse, universes with 10 spatial dimensions, realities where time branches in multiple directions, bubble universes where observation creates matter. This machine creates them all. It also creates exact replicas of our own universe with identical histories. Quantum mechanics limits the number of possible arrangements of matter within a finite volume in an infinite multiverse of bubbles. The appearance of an exact replica is mathematically inevitable. Somewhere beyond our cosmic horizon, an Earth orbits a sun located in a Milky Way galaxy. This replica has the same continents, the same life forms, and even an exact copy of you, living a life identical to yours. The eternal inflation machine ensures this cosmic duplication doesn't happen just once. It happens infinitely many times. Every possible history, every different choice, every different outcome becomes real somewhere in this infinite sea of bubble realities. Andre Land, one of the founders of inflation theory, calls this the ultimate Copernican revolution. Not only are we not the center of the universe, our entire universe is not the center of existence. The realities produced by this machine are so strange that some universes even have 10 spatial dimensions, instead of the familiar 3. Moving in 10-dimensional space would throw you into confusion within seconds. We are trapped in 3 spatial dimensions: length, width, height. Every object you see, every direction you can point, every path you can walk, is confined to this 3-dimensional cage. Your brain evolved capacities only sufficient for understanding a reality of 3 spatial dimensions plus 1 time dimension. But string theory requires at least 10 dimensions. 6 extra spatial dimensions are curled up at every point in space, too tiny for us to detect directly. It's like looking at a garden hose from afar. The hose looks like a one-dimensional line, but up close you see the line actually has width and circumference, hidden dimensions that only appear at smaller scales. The extra dimensions in string theory work similarly. At every point in our 3D space, there are 6 additional directions perpendicular to length, width, and height. These directions are beyond your ability to visualize because the human brain lacks the neural architecture to comprehend higher dimensions. In other bubble universes, the extra dimensions might not be curled up to microscopic scales. Imagine a reality where objects can move in 10 full spatial dimensions. A 10-dimensional sphere would appear in our universe as a series of constantly changing 3D cross-sections. The full form of this sphere would be invisible to us, as most of its volume extends into dimensions we cannot perceive. Life native to 10-dimensional space would have senses capable of detecting light, sound, and matter from directions that don't exist in our reality. They could approach you from a dimensional angle, making them seem to appear and disappear out of thin air. The physical laws in 10-dimensional space would be correspondingly alien. Gravity would propagate through 10 dimensions, making it much weaker at any given distance compared to our universe. Stars might not form because gravity couldn't overcome thermal pressure. Galaxies would be even more impossible to form, as gravitational attraction would be too diluted. But in higher dimensions, other forces might become stronger. Electromagnetic interactions or exotic forces predicted by string theory might sculpt matter into structures we can't imagine, following geometric patterns based on 10-dimensional symmetries that seem impossible from our 3D perspective. Advanced civilizations in 10D bubble universes would manipulate matter using principles we can't grasp. They could use the extra dimensions as data storage. Holding infinite information in a finite volume, they could traverse vast distances instantly via higher dimensional shortcuts. Some string theorists propose our 3D universe might be a brain, floating in a higher dimensional space called the bulk. Other similar brains might exist parallel to ours. They could be extremely close in the extra dimensions, yet billions of light years apart in our familiar 3D space. Gravity can propagate through all dimensions. This means massive objects in parallel universes could influence matter in our reality. This might explain the missing mass problem that astronomers attribute to dark matter. Spatial geometry is just one aspect in which bubble universes might differ from our reality. These differences might even challenge the very foundations of existence. The weight of vacuum space might exceed the total mass of all matter. In the observable universe, this statement might sound impossible, but quantum mechanics shows it's correct. What we call vacuum is actually filled with virtual particles, constantly flickering in and out of existence. Too briefly for any measuring device to catch, these quantum fluctuations create a background energy, filling every cubic inch of space. According to theoretical calculations, the energy density of quantum vacuum fluctuations should be extremely high. If you added up all the virtual particle energy in a coffee cup's volume, the total could exceed the combined mass energy of all visible stars and galaxies. But here lies a cosmic puzzle. This quantum vacuum energy should produce a powerful gravitational field, strong enough to curve space-time into a tiny ball. Our universe should have collapsed before the first atom would form. Yet, in reality, we observe a universe that is almost flat and has been expanding for nearly 14 billion years. Something must be canceling out the effect of the vacuum energy, preventing the universe's collapse. Scientists call this the cosmological constant problem that remains unsolved. In different bubble universes, the relationship between quantum vacuum energy and space-time curvature might vary. In some realities, the vacuum energy might not be canceled, causing the universe to collapse into an infinitely dense point. Immediately after formation, other bubbles might evolve with negative vacuum energy, making space expand much faster than during our universe's inflationary epoch. The most intriguing possibility is bubble universes where the quantum vacuum energy fluctuates randomly across space and time. Imagine a reality where vacuum space is sometimes heavier than matter, sometimes lighter. Regions of positive vacuum energy would curve space inward like invisible black holes. Regions of negative vacuum energy would curve space outward like cosmic anti-gravity wells. In such a universe, matter and energy would follow bizarre trajectories. As they moved through regions of constantly varying space-time curvature, stars might suddenly accelerate or decelerate, When encountering a vacuum energy fluctuation, planetary orbits might suddenly reverse or warp into impossible shapes. Advanced civilizations in a universe with variable vacuum energy would need to develop technology that could adapt to constantly changing physical laws. Their spacecraft would need navigation systems capable of handling random gravitational anomalies. Their cities would need stabilizing structures to resist fluctuations in space-time curvature. Some theoretical physicists propose that consciousness might influence quantum vacuum fluctuations through the observer effect. In bubble universes where the observer effect is stronger, intelligent life might be able to manipulate local space-time by focusing attention on specific regions. This would create universes where thought directly affects physical reality. Meditation could alter gravity. Collective consciousness could reshape the fundamental properties of space. This observer-dependent physics might exist in bubble universes that formed inside the event horizons of black holes in other realities. Every black hole in our universe might contain a complete universe inside. When a massive star collapses, it forms a region where space-time is curved so severely that not even light can escape. We call this a black hole, a cosmic vacuum cleaner that swallows everything nearby. But mathematical analysis of what happens inside the event horizon suggests something far more peculiar. The collapsing matter doesn't simply get crushed into a point of infinite density. Instead, it might trigger a new Big Bang, creating an expanding universe inside the black hole. This interior universe is completely cut off from our reality. No information can travel outward through the black hole's event horizon. From our perspective, the black hole is frozen at the moment of collapse. We cannot observe any changes inside it. But from the perspective of matter falling in, time flows normally. The collapsing matter experiences extreme tidal forces, stretched and compressed into exotic forms. Under these conditions, space-time itself might undergo a phase transition, triggering inflation. It's like a seed germinating inside a protective shell. From outside the shell, nothing seems to happen, but inside, a complex organism is growing and maturing. A black hole universe works similarly. An entire reality evolves inside the event horizon, while from an external observer's view, the event horizon remained static. The mathematics of this process suggests the universe inside a black hole could be much larger than the black hole that contains it. This seems impossible, but remember, space-time itself is curved. The interior of a black hole is a region of space-time that is topologically separate from our own. Physicist Lee Smolin proposed that black hole universes might explain why the physical constants in our universe seem fine-tuned. If universes that produce more black holes also produce more daughter universes, then natural selection would favor physical laws that allow the formation of massive stars. Our universe, through stellar evolution, has produced billions of black holes. Each black hole might give birth to a pocket universe with slightly different physical laws. Over vast cosmic timescales, this reproductive process would fill the multiverse with realities optimized for black hole production. Daughter universes might have stronger gravity or different nuclear physics. Each generation of universes becomes better adapted for cosmic reproduction. This evolutionary cosmology suggests our universe is the descendant of countless generations of black hole universes. Our physical laws exist because they proved effective at producing black holes. In predecessor universes, some bubble universes might have physical laws so efficient at producing black holes that they themselves resemble giant stellar nurseries. The number of black holes in these realities could be billions of times greater than in our universe. Each black hole could spawn new pocket universes, while black holes create pocket universes through gravitational collapse. Massive structures beyond our cosmic horizon might be pulling matter through entirely different mechanisms. An object with a mass of 10,000 Milky Ways is pulling our entire region of space towards the constellation Hydra. The Milky Way is moving through space at over approximately 1.61 million kilometers per hour. This direction cannot be explained by cosmic expansion alone. Our galaxy, along with thousands of nearby galaxies, is moving towards an invisible gravitational anchor located about 150 million light-years away. Astronomers call this cosmic magnet the Great Attractor. The truly puzzling thing about the Great Attractor is when scientists point telescopes towards Hydra, they find only seemingly normal space. There are galaxy clusters there, but nothing massive enough to gravitationally dominate our local region of the universe. Part of this object is hidden by the zone of avoidance, a band across the sky where dust in our own Milky Way blocks our view of distant objects. But even accounting for this cosmic dust curtain, observations show there isn't enough matter to explain the Great Attractor's gravitational influence. Scientists found the Great Attractor itself is being pulled by an even larger structure, the Shapley supercluster. This vast collection of galaxy clusters has a gravitational pull equivalent to 1,016 suns, concentrated in a region spanning hundreds of millions of light-years. But the cosmic hierarchy doesn't stop there. The latest maps of galaxy motions show our entire local region of the universe is participating in an even grander flow towards a structure mostly located beyond the observable universe. Scientists call this phenomenon the dark flow mentioned earlier. It suggests the Great Attractor is just a small part of a cosmic structure extending far beyond our view. It's like drifting down a river towards a waterfall. You can feel the current pulling you forward, but you can't see the waterfall itself because it's hidden around an upstream bend. The Great Attractor and dark flow act similarly. We can measure their gravitational influence on local galaxies, but the source of this gravity might extend into regions of space we can never observe. Some cosmologists propose the Great Attractor might be a massive dark matter concentration left over from the cosmic inflationary period. During inflation, quantum fluctuations could have created density variations in matter on scales far larger than the observable universe. What we observe might be just a small piece of these cosmic megastructures. Other theories suggest the Great Attractor could be evidence of extra-dimensional physics. A massive object existing in higher dimensions could exert gravitational influence on our 3D space without being visible to our telescopes. The possibility of invisible extra-dimensional objects points to quantum foundations for bubbly universes completely different from our own. In some bubbly universes, like charges attract, and unlike charges repel. This reversal would prevent atoms from forming. Protons in an atomic nucleus, all positively charged, would blow apart due to intense repulsion. No force could hold them together long enough for electrons to orbit them. Chemistry would be impossible. Molecules could never form. Life as we know it couldn't exist, but an inverted electromagnetic force might allow completely different types of matter to form. Imagine stable structures made of particles with the same charge gathering together. These same charge assemblages might form crystal-like structures. Gravitational attraction holds them together, while electromagnetic repulsion prevents total collapse. The balance between gravity and electromagnetic repulsion might create exotic matter with properties completely different from matter in our universe. These structures could be hollow, with complex internal geometries shaped by the competing forces. In a universe with inverted electromagnetism, the evolution of large-scale cosmic structures would also be drastically different from ours. Cosmic plasma would behave oppositely, possibly forming galaxies that focus matter rather than disperse it. Magnetic stars might form via electromagnetic attraction rather than gravitational collapse. In other bubble universes, the strength of the electromagnetic force could be millions of times stronger or millions of times weaker than in ours. In universes with stronger electromagnetism, atoms would be larger, and chemical bonds would have higher energy. Molecular structures could become extremely complex, perhaps even forming exotic chemical and biological forms. In universes with weaker electromagnetism, atoms would be so small that quantum effects would dominate all chemical reactions. Matter would behave more like a quantum fluid than discrete particles. Such a universe might support forms of intelligence based on quantum coherence rather than classical computation. The strangest possibility is bubble universes where the electromagnetic force splits into multiple independent forces. In these realities, there is no single electromagnetic field. Instead, the electric and magnetic forces operate independently. Civilizations in such a universe would develop technologies to manipulate electric and magnetic forces separately. They might create materials responsive only to electricity, not magnetism, or vice versa. Their electronics would follow completely different engineering principles. Some bubbly universes might contain entirely new fundamental forces absent in our universe. These exotic forces could bind matter together in ways we can't imagine, forming stable structures. Advanced life in these universes might harness forces we can't even conceive of, manipulating matter at will, instantly traversing cosmic distances, or transforming energy into complex information patterns. This diversity of electromagnetism is just one aspect of the infinite variety in the eternal multiverse. And this electromagnetic diversity might be interconnected through a dark matter network spanning multiple bubble realities. Dark matter might be the cosmic internet connecting infinite realities. In our observable universe, galaxies cluster along invisible filaments of matter, extending for billions of light years. These dark matter structures form a cosmic web, connecting galaxy clusters and guiding the flow of ordinary matter through the cosmos. We can map this web by observing how the gravity of dark matter bends the light from distant galaxies. Dark matter filaments act like mass highways, channeling matter and energy across the universe. Without this scaffolding, galaxies would be randomly distributed in space, not forming the beautiful large-scale structure we observe. But the revolutionary possibility is this cosmic web might extend beyond our observable universe into other bubble realities. If dark matter formed during the inflationary period before bubble universes separated, then the same network of dark matter filaments might span multiple realities simultaneously. This would establish a physical connection between otherwise causally disconnected bubble universes. It's like the underground fungal network connecting trees in a forest. The trees appear separate above ground, but the subterranean root network allows them to share nutrients and information. Bubble universes might be similarly interconnected via a dark matter network. Gravitational effects could travel along these dark matter filaments from one bubble universe to another. This might explain mysterious phenomena like the dark flow. Galaxy clusters in our universe seem pulled by massive structures beyond our view. The dark matter network might also provide a mechanism for information transfer between realities. Gravitational waves traveling along dark matter filaments could carry encoded information from advanced civilizations in different bubble universes. Some theoretical models suggest dark matter exists in extra dimensions you cannot directly perceive. These higher-dimensional dark matter structures might intersect with multiple 3D bubble universes simultaneously, establishing gravitational links between different realities. Advanced civilizations might learn to manipulate dark matter filaments as a form of cosmic engineering. By concentrating or dispersing dark matter in specific patterns, they could alter the gravitational environment around star systems, or even artificially create passages connecting to neighboring bubble universes. The cosmic web could become a transportation network for traversing bubble realities. If dark matter filaments can sustain stable wormhole-like connections across the inflating multiverse, these structures could serve as highways for inter-universal exploration. Mapping the full extent of the cosmic web could reveal which bubble universes are still connected to our reality and which have become completely isolated. This information would help scientists understand the topology of the multiverse and predict the evolution of bubble universes. The dark matter web is our greatest hope for probing and perhaps even communicating with other realities. But intelligent life in some bubble universes might be so advanced that they create new realities through conscious observation. Consciousness might be the most powerful force in the multiverse. Quantum mechanics suggests the act of observation can fundamentally change reality. Before measurement, a particle exists in multiple states simultaneously. The famous double-slit experiment shows an electron can pass through to different paths at once until someone observes which path it actually took. This observer effect suggests Consciousness plays a direct role in determining physical reality. In our universe, conscious observation has negligible impact on large-scale phenomena. You can't move mountains by thinking, or change a planet's orbit by meditation in warm environments. Quantum effects become negligible for massive objects, but other bubble universes might have evolved where quantum effects are strong at all scales. Imagine a universe with no boundary between the quantum and classical worlds. In such a reality, conscious observation could directly influence stars, galaxies, even space-time itself. Intelligent life might be able to think matter into existence, or reshape cosmic structures through focused intention. The mathematics of quantum mechanics allows this possibility. If environmental decoherence doesn't destroy quantum superpositions, then objects of any scale could exist in multiple states simultaneously until consciousness collapses them into a specific reality. Civilizations in observer-dependent universes would develop along paths completely different from our world. Instead of building tools to manipulate matter, they would train their minds to manipulate reality. Their technology would be based on consciousness, not engineering. These beings might create matter through imagination, teleport by observing themselves in distant locations, or even alter fundamental physical laws through collective consciousness. Their societies would be built on the understanding that reality responds to consciousness. Some cosmologists propose the existence of consciousness might be necessary for the universe to exist. This participatory anthropic principle suggests a reality without observers would be trapped in quantum superposition, never forming definite classical properties. If this theory is correct, then bubble universes without consciousness would exist only as ghostly quantum possibilities, not concrete realities. Only bubbles that evolve intelligent life would collapse into definite physical states. This creates a selection effect. Conscious observation becomes the deciding factor for which possible universes can truly exist. The multiverse would be composed primarily of realities that permit consciousness. Advanced conscious beings might learn to observe other bubble universes, thereby bringing them into reality. By focusing on specific quantum possibilities, these cosmic observers could create new realities through attention. The observer effect could also explain why our universe seems fine-tuned for life. If consciousness is necessary for reality to exist, then all observable universes must have conditions that allow consciousness to develop. The relationship between consciousness and reality becomes even more profound when you consider that our entire universe might be a simulation run on a computer in another reality. Your entire existence might just be code written by beings in a higher level reality. The simulation hypothesis proposes that the physical reality we experience is actually a detailed digital simulation created by an advanced civilization. Every atom, every star, every thought in your brain might be a computational process in a giant cosmic computer. This isn't just science fiction speculation. The mathematical basis is strong. Any civilization that develops sufficient computing power could simulate an entire universe in detail. If such simulations are possible, then the number of simulated realities would likely vastly outnumber the one base reality. Statistically speaking, we are more likely to be living in a simulation than in the base reality. Applying this concept to the multiverse makes it even more mind-boggling. If our universe is a simulation, then the computer running it exists in another universe, and that universe might also be a simulation run on a computer in a yet higher reality. This creates a hierarchy of nested realities, like Russian dolls. Each level simulates the one below it. The simulated lives within our simulation might themselves be simulated beings in a higher reality, and those higher-level beings might also be simulations in a more fundamental universe. This chain could extend through countless layers of computation. Each level of simulated reality has limited computational resources. The base reality can utilize the full computational resources of physical matter. Each nested simulated reality has reduced resources because some computing power must be used to run the simulation itself. This sets a natural limit on the number of simulation layers. Eventually, computational demands would exceed available resources, preventing deeper levels of simulation. But civilizations might overcome these limits. They could develop more efficient simulation algorithms, or build larger computers. Advanced beings might even learn to harness physical processes in reality to achieve infinite computing power. A civilization with universe-spanning quantum computers might run infinite simulations simultaneously by leveraging the quantum superposition of parallel universes. The simulation hypothesis could also explain why our universe has fundamental limits like the speed of light and the quantization of energy. These might be shortcuts programmed into the simulation to reduce computational load. The physical constants might represent the resolution limits of the cosmic computer running our reality. Just as video games use simplified physics to save computational resources, our universe might use approximations of fundamental laws to avoid excessive computational cost. If we live in a simulation, we might be able to detect glitches or signatures that reveal its computational nature. Scientists are searching for such evidence. For example, pixelation of space-time at the smallest scales, or computational limits in the complexity of quantum systems. The simulation hypothesis is just one possible explanation for our existence, but the ultimate answer might involve an eternal cycle of creation and destruction of infinite realities. Our universe will meet its end only to allow the birth of infinite other universes. Each bubble universe follows the same cosmic life cycle, born via inflation, evolving through expansion and cooling, and eventually dying through heat, death, or collapse. But within this end lies the birth of countless new realities in an endless cycle of cosmic reproduction. Here is how our bubble universe will end. Dark energy continues to accelerate cosmic expansion, causing galaxies to recede from each other faster and faster. Eventually, expansion will push each galaxy beyond the other's cosmic horizons. Each galaxy will be isolated in its own pocket of space, unable to observe or influence any other cosmic structure. Stars will exhaust their nuclear fuel and die, White dwarfs will cool into cold black dwarfs if theory is correct. Neutron stars will dissipate via proton decay. Black holes will evaporate via Hawking radiation, a process so long that the current age of the universe is but a fleeting instant in comparison. The final state of the universe will be a cold vacuum with only elementary particles separated by distances larger than our current observable universe. This heat-death state represents maximum entropy. No physical process can extract any more energy, but the universe's story doesn't end with heat death. Throughout the decay and cooling process, quantum fluctuations in the vacuum never cease. These fluctuations occasionally create regions of false vacuum, which can trigger new inflationary events. The heat death of our universe provides the calm, low-energy environment, perfect for new universe seeds to germinate. It's like a forest fire clearing deadwood, creating conditions for new saplings to grow. The end of our universe paves the way for the evolution of the next generation. Roger Penrose proposed a more dramatic cyclical theory, conformal cyclic cosmology. In this model, the heat death of our universe is the Big Bang of the next cosmic cycle. The geometric properties of space-time allow the infinite future of a dying universe to smoothly connect to the birth moment of a new universe. Each cosmic cycle resets the clock of time, yet preserves some information from the previous universe. Certain patterns in the cosmic microwave background might carry information from the universe before our Big Bang. This eternal cycle ensures cosmic evolution never ends. Death and rebirth alternate endlessly. The end of each universe provides the possibility for the creation of countless new realities. Some of these new universes might have physical laws identical to ours. Others will explore entirely new possibilities, and this cosmic reproduction might be driven by consciousness itself. If consciousness can influence quantum processes, then the evolution of intelligent life in a dying universe might determine the properties of subsequent universes. Advanced civilizations facing cosmic end might encode their knowledge and culture into quantum fluctuations, influencing the formation of new universes. In this way, consciousness could achieve a form of immortality by shaping the infinite future realities. This eternal cycle transforms cosmic endings into new beginnings. The inevitable demise of our universe becomes the fertile ground for infinite cosmic creativity beyond our cosmic horizon. This cycle plays out eternally, creating infinite realities, where every possibility becomes real, every dream is realized. At the other end of the universe, it's not just more space, it's infinite kinds of existence itself. All right, my friend, let's pause our conversation here tonight on the mysteries of the universe. Now, allow me to press pause for you. Set aside all thoughts and inquiries, and simply, quietly be in this moment. From here, my voice will fade away, leaving only the silent tapestry of the cosmos and a carefully chosen piece of pure music tuned to 432 Hz. Science suggests this frequency resonates deeply with the natural vibrations of the universe and the rhythm of life itself, soothing your nervous system and guiding you into deep relaxation. Now, find your most comfortable position Gently close your eyes or let your gaze rest softly upon the stars. May you release all weariness from the world, letting your consciousness drift on the waves of music, floating into boundless tranquility. Good night, sweet dreams, until we meet again among the stars.